Now let's discuss the image-to-video workflow. As the name suggests, image-to-video involves adding an initial image to the text-to-video process. The model will use the provided prompt and develop the video based on this image as a starting frame. Personally, I find image-to-video more commonly used than text-to-video. First, it introduces less randomness, allowing you to specify the initial frame of the video and avoid the need for repeated re-rolling. Second, it simplifies prompt, as you don't need to spend effort describing the scene in detail, just concentrate on the dynamics. Third, it lets you use image generation models to ensure the consistency of characters and backgrounds across multiple videos, which is especially handy for making sequential video clips. I'll use Wan 2.1 as the demonstration model and load its image-to-video workflow. Compared to the 6-step text-to-video process, the image-to-video flow makes a few adjustments. Added image input and processing. The size of the processed image becomes the output video size. The prompt input section is enhanced with clip vision model processing results. The model aggregates this result with the text prompt to determine subsequent video frames. Otherwise, most steps are identical to text-to-video. Specifically, Wan 2.1 does not distinguish between high-noise and low-noise models, but does differentiate between text-to-video and image-to-video, as well as 480p and 720p output. For this demonstration, I selected the 480p image-to-video model's FP8 quantized version. Image-to-video has many useful LoRA models for adding special effects to the initial image. Here, I've loaded a squish-effect LoRA, but during execution you can replace it with any other LoRA you need or simply disable the node. Select Clip and VAE models according to requirements. I want to highlight the Clip Vision model used here, Clip Vision H, which is VI-TH architecture. This multimodal model encodes the reference image as a vision embedding, enabling the main model to understand the content of the reference image. The acceleration and optimization setup in this workflow differs from the Wan 2.2 text-to-video process, mainly relying on TeaCache's caching mechanism to skip part of the sampling calculations and using Enhance-A-Video for post-processing to enhance video quality. These steps are based on my own experience and are suited to Wan 2.1's image-to-video workflow, but you can substitute or combine different optimization and acceleration nodes as needed. We use the image upload node to load an image. Before passing it as the initial frame to the model, one crucial step remains, adjusting the image size. If the uploaded image matches the target aspect ratio, the process is straightforward, just scale up or down to fit the model's accepted dimensions. The algorithm recommends using Lanczos scaling, but if issues occur during downscaling, you can switch to the area algorithm. Image-to-video requires high-quality initial images, avoid using blurry pictures. If the aspect ratio doesn't match, you need to process the image, typically with one of three methods. Crop. Cut out a portion of the image proportionally. You can set the crop area, center cropping is the default. Stretch. Scale the image directly to the target size without maintaining the original aspect ratio. This will certainly cause distortion. Pad. Fill the surrounding area of the image to achieve the target ratio. There are 3 different padding strategies: pad, pad edge, and pad edge pixel. My advice is to match the input image aspect ratio to the target videos as closely as possible. If that's not feasible, I prefer cropping and manually selecting the crop area to keep key content. Image-to-video prompts are relatively simple. Just mention the key entity in the image and focus on the desired dynamic effect and camera movement. In our workflow, the prompt was written as recommended by the LoRA author. It precisely describes using 2 hands to squish the character. The negative prompt covers only image quality aspects, which can be left unchanged in most cases. The sampling section contains 2 nodes. The preceding node processes the positive and negative prompts, vision embedding info of the initial frame itself, VAE target dimensions, and frame count. Since we're generating a 5-second video, we need 81 frames. This node prepares the instructions and 81 latent images. The sampling node uses K-sampler. Like in text-to-video, main parameters include steps, CFG, sampling method, and scheduler. For most models, increasing the steps improves quality but also extends runtime. CFG is best left at its default value. Sampling method and scheduler can follow the official recommended combination or use the general-purpose Euler pas simple. After sampling, we need to use VAE to decode all latent images into frames and combine them into the final video. Be sure to keep the output FPS consistent with the models. Wan 2.1 uses 16. If VRAM usage is excessive during decoding and you encounter OM errors, you can switch to tiled decoding node. This trades space for time, significantly reducing VRAM usage, but may introduce visible seams during tile stitching. After clicking Run, we obtain the finished video, and the effect is quite interesting. We don't have to rely on LoRA. The base model can directly animate the character in the input image, such as waving, walking, or crying. You can also turn an anime image into a short animation, or even try achieving imaginative interactive effects. The demo above used Wan 2.1, but with models such as Wan 2.2, LTXV, Wan Video 1.5, etc., the overall workflow remains essentially the same. Just select the proper model during loading and follow specific prompt and parameter recommendations for that model. No other modifications are needed. The approach converges to the same result. In summary, image to video is one of my favorite workflows, stable, controllable, and yielding excellent results. I hope you find it useful and can turn your creativity into finished works.